Assalamualaikum and a very good day. We are from Group 6, would like to explain more on ionization chamber dosimetry. These are the contents that we will discuss more on further slides. Hi, my name is Nur Syaratul Adiba and I will talk about the introduction of the ionization chamber dosimetry. Ionization chamber is an air-filled ionization which is the workhorse for reference dosimetry in radiation therapy clinics. They have well-established characteristics such as ease of use, long-term stability, high signal-to-noise, and linearity. Medical physicist is responsible on patient dosimetry in diagnostic radiology. Meanwhile, dosimeter is used to measure dose of ionizing radiation, and it can be divided into two types, which are active and passive dosimeter. Deionization detector is an air-filled chamber in which an electric field is formed by the application of a polarizing voltage across two electrodes to collect all charges liberated by the ionization of the air contained within the chamber. The electric field is sufficient to collect almost all of the charges that reach the electrodes, but insufficient to induce gas charge multiplication and collision ionization of other molecules. The number of ions collected or the rate of their charges is the recorded signal. This charge is read out by the electrometer and may be converted to absorb dose and used to determine the radiographic exposure expressed in coulomb per kilogram or Röntgen. And the figure below is the visualization of the operation of a parallel ion chamber. Next, I will pass to Atika for the next content.
Okay, hi, my name is Atika. Okay, now I will continue with the next part, which is the basic working principle of the ionization chamber. Before proceeding, I would like to summarize a bit about the principle of an ionization chamber. An ionization chamber measures the charge from the number of ion pairs created within a gas caused by incident radiations. It consists of gas-filled chamber with two electrodes, an anode and a cathode, in which a voltage is applied to maintain an electrical field that is held at the same voltage. And the device is characterized by a capacitance determined by the electrode's geometry. It starts when a voltage potential is applied between the electrodes to create an electric field in the field gas. The applied voltage is high enough to allow the complete collection of positive and negative ions. When the gas between the electrode is ionized by incident ionizing radiation from the source, either from X-ray, gamma rays, or electrons, it creates a finite number of ion pairs, and the positive ion and electron forms under the influence of the electric field. The resultant positive ion and electron move to the electrodes of the opposite polarity, where the negative charges are attracted by the anodes and positive charges by the cathode. This causes an ionization current, which is then measured by an electrometer circuit. The electrometer must be capable of measuring the very small output current depending on the chamber design, radiation dose, and the applied voltage. Next, we proceed to the types of ionization chamber. There are few types of ionization chamber dosimeters. This includes cylindrical ionization chamber, or known as thimble type ionization chamber, parallel plate ionization chambers, brachytherapy chambers, or well type ionization chamber, and the last one is free air ionization chambers. So, let me explain to you all this ionization chamber one by one. Let's go. First is a cylindrical or thimble type ionization chamber. This type of ionization chamber consists of a central electrode and a cylindrical chamber wall with a spherical end mounted on a cylindrical stand. A guide on central electrode potential leading up to sensitive volume limits that currents and stand effects. This is the most popular design as is independent of the beam direction. The typical volume, radius, and length are as listed here. The thimble type ionization chamber is used for electrons, photons, protons, or ion beams and is recommended for beam calibration. There are three different types of cylindrical ionization chamber, including Farmer ion chamber, semi-flex ion chamber, and pinpoint ion chamber. Next is the parallel plate ionization chamber. This ionization chamber consists of two plain walls. One acts as an entry window and polarizing electrode, and the other as the back wall and collecting electrode as well as a guard system ring. The back wall is usually a block of conducting plastic or a non-conducting material, usually perspex or porosity, with a thin conducting layer of graphite forming the collecting electrode and the guard ring system on top. It is recommended for dosimetry of electron beam with energy below than 10 MeV. It is also used for surface dose and depth dose measurement in the build-up region of megavoltage photon beams. Monitor chamber and extrapolation chambers are typically parallel plate ionization chamber that are used to continuously measure such as a radiation beam's intensity. The next is brachytherapy chambers or well-type ionization chambers. A well-type chamber consists of an outer housing with an inside cylindrical cavity that represents the chamber wall and functions to receive the measuring object. A guard on the central electrode potential around the measuring electrode stem limits the dark current. Sources used in brachytherapy are low air kerma rate sources that require chambers of sufficient volume for adequate sensitivity. Well-type chambers are ideally suited for the calibration and standardization of brachytherapy sources. High sensitivity is useful for low-rate sources as used in brachytherapy and large volume. This type of ionization chamber can be designed to accommodate various sources size and is usually calibrated in terms of the reference air kerma rate. Two types of well-type ionization chamber are used in the calibration of brachytherapy sources. There are high-pressure gas-filled well-type ionization chambers and well-type ionization chamber that are open to the atmosphere. Okay, the last one is free air ionization chambers. This ionization chamber you operate usually below 1000 keV and strictly follows the definition of exposure. It is intended mostly for gamma ray measurement. The free air chamber is a standard of exposure and is used as a standard of air kerma by using the energy required to create an ion pair in the air. The free air chamber is an ionization chamber without walls as is freely open to the atmosphere, where the filled gas is ambient air. The domestic smoke detector is a good example of this, where a natural flow of air through the chamber is necessary so that the smoke particles can be detected by the change in ion current. There are different types of free air ionization chambers. The models which are the most used are the free air ionization chamber with parallel plates, also called as conventional model, and the free air ionization chamber with concentric cylinders. I will pass to the next presenter, Nur Farahim.
Hello everyone, my name is Nur Farahim Jahrana binti Muhammad Nasser and I will be presenting about dosimetry properties of ionization chamber. Let's go! The dosimetry properties that I will talk about is about the sensitivity, energy dependence, directional dependence, leakage current and the correction factor. Sensitivity is the minimum air kerma required to produce a signal output by the detector and collected by the measuring assembly. The better the sensitivity of the dosimeter, the higher the current produced. In overall, will produce better resolution and detectability. Sensitivity is directly proportional to the chamber sensitive volume. Therefore, the ionization chamber with larger active volume exhibit higher sensitivity than those with smaller volumes. Meanwhile, the kerma rate is inversely proportional to the volume. Hence, large ionization chambers are preferred for low air kerma rate, such as in fluoroscopy or for scattered radiation. Meanwhile, in radiography, the air kerma rates are higher with smaller chamber volume. Next is the energy dependence. Energy dependence means the variation in the dosimeter response with varying energy. This depends on the detector type and its physical and structural properties. The variation in response to different radiation qualities is considered using a beam quality correction factor KQ. The image shows that the duration of energy response is between 50 to 150 kV range for ionization chamber. So the response of a dosimeter may vary when the radiation is incident on the detector from different angles. So for example, we can see here is the directional dependence of plane parallel ionization chamber. So for example, here at 90 degree, it is at a dose of 104. At 180
180 degree it is at 94, at 270 degree it is at 104. The directional or angular dependence primarily depends on the detected construction and physical size or the energy of the incident radiation. Next is the leakage current. Leakage current refers to any signal change recorded by the measuring assembly that is not generated by the radiation. This could be by electronic noise, current from resistor capacitor circuits, damaged cables, or the bad cable connection. The leakage current should not exceed 5% of the minimum effective air current rate. The next correction factor is called the polarity effect. The polarity effect is caused by the changes in magnitude as the polarity of the collecting voltage is reversed. The errors caused by polarity effect can be minimized but cannot be eliminated. Therefore, the polarity effect should be less than 0.5% for any radiation beam. The next correction factor is called the ion recombination factor. The ion recombination correction factor, or also known as p-ion, is defined to account for incomplete collection of charges, and it is a function of dose per pulse. P-ion is also known as the ratio of the number of ions collected to the number of ions produced. The chamber bias voltage should be within the saturation region to minimize the recombination losses. To determine the ion recombination correction, which is p-ion, select two bias voltage V1 and V2, such as V2 equals to V1 over 2, and take the electrometer reading with them. The ratio of the readings Q1 over Q2 is rated to the p-ion. Ion chambers with p-ion more than 1.05 should not be used because of the uncertainty in the p-ion value, whereas bias voltage should not be above 300 volt. So for the ionization dosimetry properties as that is discovered by a new research is the ionization chamber dosimetry in ultra-short pulse high dose rate, very high energy electron beams. So high dose rate radiotherapy, or also known as flash, has been shown to increase the differential response between healthy and tumor tissues. Moreover, very high energy electrons VHEE provide more favorable dose distribution than conventional radiotherapy, electron and photon beams. Therefore, we use plain parallel ionization chamber, which is recommended as the secondary standard system for clinical reference dosimetry of electrons. Therefore, the aim of this study is to determine the relationship between the recombination factor of an ionization chamber and a wide range of dose per pulse values for an electron linac with higher instantaneous dose rate. So the absolute dose per pulse was measured with a designed graphite calorimeter compared to dose obtained from PTWROOS ionization chamber. As the calorimeter measurement system is dose rate independent, it was possible to determine the recombination factor of the ROOS chamber. So the recommended recombination correction procedure for this study is the validity of both analytical models proposed by Bock and Demart. Additionally, a logistic model for the recombination in high dose per pulse beam used by Peterson has also been investigated. This manuscript provides a groundwork for future developments of ion chamber-based dosimetry of flash and ultra-high dose per pulse. The result of this study showed that better normal tissue sparing is obtained by delivering a lower number of pulses and hence higher dose per pulse, which will decrease the collection efficiency in ionization chamber. This study provides a groundwork on which a wide variety of further dosimetric studies in high dose per pulse radiation, including laser plasma accelerator, VHEEs, and electron and proton flash radiotherapy, can be conducted. The next presenter will be Fatima, and she will be presenting about the ionization dosimetry properties. Thank you for watching this. That is all from me.
My name is Fatima Zahara, and I will continue to explain more about dosimetric properties of ionization chamber. In this part, I will explain about dose rate dependence, accuracy and precision, spatial resolution and physical size, also readout convenience and convenience of use for ionization chamber. Another properties of ionization chamber is dose rate dependence. A detector's reading may also depend on the dose rate. Integrating system measure the integrated response of a dosimetry system, and for such system, the measured dosimetric quantity should be independent of the rate of that quality. Ideally, the response of a dosimetry system, M over Q, at two different dose rates should remain constant. For an example from the experiment of dosimetric parameters investigation of the pulse X-ray and gamma radiation sources, the graph shows the dependence between the dose rate of the pulse X-ray beam and anode current, where the first line is data from the thermoluminescent dosimeters, second line is planned parallel ionization chamber, and the third one is for dosimeter radiometer. From the graph, it shows that the dose rate measurement obtained with the help of these three dosimeters in a good agreement and can be used for dosimetry measurements of the pulse X-ray generator. Because of dosimeter reading is affected by doses rate, an appropriate correction factor are necessary. For example, recombination corrections for ionization chamber in pulse beam. And then we have accuracy and precision for ionization chamber. In radiography dosimetry, the uncertainty associated with the measurement is often expressed in terms of accuracy and precision. The precision of dosimetry measurement specifies the reproducibility of the measurements under similar conditions and can be estimated from the data obtained in repeated measurements. Uncertainty is a parameter that describes the dispersion of the measured values of quantity. There are two types of uncertainty, which are evaluated by statistical methods, type A, and the uncertainty of an input component cannot be estimated by repeated measurement, which is type B. Taking an example of a sealed ionization chamber with 4 liter volume and wall of 3 mm thickness from Wakatsuki, we can see a lot of data for accuracy and precision. The data include are the error in measurement practice, error in correction as a systematic error in calibration, and the reproducibility of the instrument, which is deviation, the accuracy of measurement system, and lastly is the total standard deviation. And this total standard deviation is obtained in careful practice, and normally it is supposed to be 10%. Next, we have spatial resolution and physical size properties. Since the dose is point quantity, the dosimeter should allow the determination of the dose from a very small volume. For an example, one needs a point dosimeter to characterize the dose at a point, and the position of the point where the dose is determined, such as its spatial location, should be well defined in a reference coordinate system. For our dosimeter, which is ionization chamber, it has a finite size to give the required sensitivity, although the new type of pinpoint microchambers partially overcomes the problem. Lastly, readout convenience and convenience of use for ionization chamber. Ionization chamber are direct reading dosimeters and generally more convenient compared to passive dosimeter, where the passive dosimeter is read after due processing following the exposure, such as thermoluminescent dosimeters and films. Ionization chambers also can measure in both integral and differential modes. Another property that we can see is ionization chambers are reusable with no or little change in sensitivity within their lifespan. That is why ionization chambers are quite rugged dosimeters. That's all from me. I will pass to my friend, which is Siti Aisyah, to continue about clinical use of ionization chamber in radiation field.
Assalamualaikum and hi, I am Siti Aisyah and I would like to further explain about the application of ionization chamber dosimetry. First, I would say that ionization chamber dosimeter, or IC for short, is widely used for medical and industrial application. As a medical physics student, I would like to touch about the application of IC dosimeter in medical or precisely clinical application. First, IC is commonly used for diagnostic radiology. It has become a tool to determine achroma or dose, such as for radiography, fluoroscopy, or mammography. Type of IC that are used to perform this are usually cylindrical or parallel plate. In mammography, parallel plate IC being used has a thin entrance window and made of a low-density material such as acrylic. It was placed perpendicularly to radiation beam. Did you know that parallel plate chambers are disc-shaped with diameters of several centimeters and thickness of few centimeters? This is why it can be safely inserted in hollow spaces such as X-ray table under a phantom in contact with the image intensifier or inside film cassette holder or bucket. The effective volumes or air cavity that are suitable for application in a wide range of exposure rates are from 1 to several hundreds of centimeters cubed. Cylindrical pencil type ionization chamber is used for CT or dental application to measure air kerma length product. It is positioned with its axis perpendicular to the central beam axis. It will be partially irradiated unlike other detectors. The response of active volume should be uniform along its entire axial length. Ionization chambers has also become air kerma area product or KAP chambers. The criteria are to have a large surface area and transparent to radiation and light. It measures the integral of the air kerma over the area of the chamber. It measures the incident radiation or the transmitted radiation and also being used for patient dosimetry in interventional radiology, fluoroscopy, general radiography, and pantomographic dental radiography. This is why KAP is recorded for Diagnostic Reference Levels or DRL. However, it should be calibrated in situ due to the presence of off-focus and scattered radiation. Next is for health physics instrument which is being used for both medical and industrial radiography. Ionization chamber that is being used is called pocket IC dosimeter. It must be worn all the time by the one working with the radioactive source, especially for radiation protection officer or RPO, physicists and radiation workers because each of them has radiation exposure limit. It can provide info about the dose or dose rate at that particular location. It can detect gamma at 5 to 200 milliroentgen ranges. Pocket IC dosimeter is made of quartz glass fiber that is embedded in air-filled ionization chamber. In the chamber, at one end is metal electrode attached to a terminal and the other end is quartz fiber. Ionizing radiation pass through the chamber, ionize the air and create electron-ion pairs and reduce charge on electrode. Quartz fiber would move towards the electrode and the amount of radiation dose is determined by the amount of the movement. Next, I would like to explain about the clinical use of IC in radiotherapy field. For your information, ionization chamber has been integrated permanently in the neck head. The type of IC being used for the neck for the latest generation is dual transmission ionization chamber. The function is to monitor the beam output continuously during treatment, monitor the primary dose in MUs, beam energy, flatness and symmetry, and the secondary chamber would terminate irradiation if primary chamber fails if the dose given exceeds the prescribed dose for safety. IC also being used for the verification of the delivered dose. A metric IC detector will be used. It measures the ionization from one point to one point and then it will be converted to a grayscale image of 256 x 256 pixels. The detector will be attached to the LIDAC arm. IC is also commonly applied for the calibration of photon and electron beam in radiotherapy. It can act as absolute or relative dosimeter. There are three types of IC that may be used in reference dosimetry. One of it is the standard free air IC, which the ions are collected in a defined volume of air. It measures the air kerma for the photon energies below 0.3 MeV. The second one is the cavity IC, which the ions are collected inside a cavity. It measures the air kerma for 0.6 to 1.5 MeV energies. The third one is the phantom embedded extrapolation chamber, which is an uncalibrated air volume extrapolation chamber built as an integral part of a water equivalent phantom. It measures the absorbed dose for megavoltage photon and electron beams. Ionization chamber is also a part of the accepting and commissioning test for the radiotherapy unit. This procedure is a series of measurements after installing a therapy machine. Some of the acceptance tests that use IC are performing a radiation survey in all areas outside of the treatment room and to detect collimated and heat leakage. It is also to verify radiation isocenter. The commissioning measurements that use IC are measuring central axis percentage depth dose and determine the collimator scatter correction. That's all for my part. Next presenter would be my friend Adiba for advantages and disadvantages.
Hi, I'm back again to list out the advantages and disadvantages of IC. Ionization chamber consists of advantages and disadvantages. The advantages of ionization chamber are recommended for beam calibration and instant readout, in which we can directly retrieve the information or data from the connected electrometer. It is also necessary corrections well understood and accurate and precise in measuring. For the detection of neutron, we use gas boron trifluoride instead of air in the chamber to detect neutron. Lastly would be the current mode. The ionization chamber has no dead time for this reason, and it is used for high radiation dose rates. For the disadvantages, ion chamber required connecting cables, which it need extra cables to connect the ion chamber to the electrometer, and it need a high voltage supply. Next, accredited dosimetry calibration laboratories (ADCLs) calibration required to calibrate user of ionization chambers against the national reference standards for clinics to calibrate the higher energy photon and electron beams of the linac. It also has limitation of size and a low density. By using gamma rays, deposit a significantly lower amount of energy into the detector than other particles. Using high pressure gas can further increase the efficiency of the chamber. Lastly, there is no charge amplification. Detectors in ionization region operate at a low electric field strength, selected such that no gas multiplication takes place. That is all from us. Thank you. Hope you all enjoy our video. And these are the references that we use.